is joining us to present his work on off-board perception for autonomous driving. So Charles is currently a senior research scientist at Waymo, and before joining Waymo, he was a postdoctoral researcher at Facebook AI Research, and he's finished his PhD with Leonard Gibas from Stanford University, and his focus is mainly on deep learning, computer vision, and 3D deep learning. And he has a list of publications in CVPR, ICCV, SIGGRAPH, Asia, and Europe's. Some of his key work is in the area of 3D deep learning, 3D object detection, and his work has been widely adopted. His key work is in the field that is known as PointNet, Frustum PointNets, and has been recognized among the top 10 influential papers in CVPR 2017 and 2018. His paper on deep huff voting has also won the ICCV 2019 Best Paper Nomination Award. You can find more of his work on his homepage. So Charles, please.
Yeah, thank you for the introduction. I'm really glad to be here today. So today we will talk about off-board perception for autonomous driving. So can everyone see my screen?
Yep.
Okay, cool. So let's start. So we know that 3D applications such as autonomous driving require lots of 3D labels for both model development and evaluation. I think one approach to tackle that is, as Xin Shuo has mentioned, we can use simulated environment. But still, real data has its value in terms of covering long-tail objects and scenarios. In order to use those real data, we require 3D labeling. However, this labeling process is very costly in both time and money. For example, annotating a 20-second sequence with full labels for every types of objects can easily take a human annotator several days. So to scale up the system, we need more automation. Can we push the limit of machine labeling models, or machine learning models, to generate near human quality auto labels? Is it possible that we can develop some offline or off-board version of perception that is more powerful? More broadly, when we think about perception for autonomous driving, most of the attention has been on the onboard use cases, where the perception is running on some onboard hardware giving real-time results for the autonomous driving vehicle. However, the perception can also be used in many off-board use cases, such as for data mining, for perception model training in the distillation case, or for behavior prediction model training, planner evaluation, or in simulation. Those use cases can have very different requirements for the perception compared to the onboard scenario. So it makes more sense for us to have another stack of offboard perception to serve those purposes. This offboard stack can share many modules with onboard one, but also has its specializations. The offboard version could be more flexible in terms of input formulation, compute latency constraint, and also the problem formulations. Our recent work published in the CVPR 2021 is one of the first steps towards building offboard perception, with a focus on 3D object detection. The paper is titled Offboard 3D Object Detection from Point Cloud Sequences, which is the work we did with my collaborators at Waymo. So why can we do better in the offboard scenario? Well, most existing 3D detectors only use point clouds from a single frame or a few history frames as their input. We notice there is much more information in the sequence data. Different frames capture complementary views of the objects. If we aggregate the object points across time, as the figure shows, we can get much denser point clouds and more complete geometry. For example, given one frame in this top-down view of this minivan, we can only see the back and left side of the car. But as we travel through time to aggregate its point clouds across different frames, we can get much more complete geometry. When we have all the 146 frames we observe this minivan, we can get almost 4 sides of this car. So we can estimate its geometry much more accurately. So considering aggregating points across frames, a naive baseline would be using multiple frames as input to the existing detectors to use them as multi-frame detectors. For example, given a current frame, we can take the history 1, 2, 3, 4, or even 5 frames to combine it with the current frame points. Given the known sensor poses through localization, we can easily transform the point clouds from a few history frames to the current frame coordinate and encode their temporal frame index with some temporal encoding channels in the point clouds. However, doing so gives us quickly diminishing returns as we increase the number of input frames. As the figure shows on the bottom right, the x-axis is the number of input frames to a detector, where we retrain the detector for each input frame's cases. And the y-axis is the 3D average precision for vehicles evaluated on the Waymo Open Dataset. So we can see as we increase the number of frames, the returns are diminishing. And another downside is that as we have more frames, it increases the compute and RAM usage by a lot. So considering the case when we have 10 frames point clouds, the number of input points are tenfold. So the early layers, which are also the heavy layers, will consume much more time and RAM to process those point clouds. The underlying cause for this inefficiency is that we aggregate information across the entire frames. While some objects may appear in up to 100 frames or more, while some other objects only appear in 3 or 10 frames. Setting a fixed frame context size cannot adapt to different objects. To address this issue, instead of aggregating temporal context over the entire frames, we can aggregate information for each object, such that we can leverage all sensor data captured for an object. This also opens doors for new algorithm formulations. The downside is that we'll need to rely on detectors and trackers to collect object information as object tracks. However, with fast advances in detection modules, we believe this is not a bottleneck. So under this idea, we built an off-board 3D object detection pipeline. From the point cloud sequence input, we first run an off-board multi-frame detector to localize objects in the scene. And then we can use a multi-object tracker to link detections across frames to form object tracks. Next, we have a unique module to aggregate object points from their tracks across all frames. So for static objects, we would use the sensor poses to align all the points into the world coordinate, such that we have natural aggregated points for those static vehicles or other objects. So those can be very dense points because we cover all the frames where this object appears. As the visualization here shows, for this car, it appears in 109 frames. We can get more than 80,000 points by aggregating its points across frames. And the geometry is well covered. For dynamic objects, since we don't know their inherent motion between each frames, we would have a trajectory instead of directly aggregated points. The full trajectory can help us estimate its heading and refine its smooth center locations. For the trajectory, we still keep its point cloud at each frame, as well as their detector boxes. We take a divide and conquer approach to process those two types of objects separately, where we use the object track-based state estimation to classify the motion state of the tracks into static and dynamic ones. Because we have access to the whole track information, the classifier accuracy is very high, approaching 100%. Actually, it's 99% beyond. And then for each type of tracks, we have specialized neural networks to refine the boxes based on the track data. The final output are the accurate and consistent 3D bounding boxes of the objects across the sequence. I want to elaborate a bit more on how we refine object shapes from its track data. So for statical ones, the aggregated points are naturally aligned. The key is to select a good coordinate system for which we can use the box coordinates from the highest score frame, such that the center of the coordinate is the box center and the x-axis is the heading of the box. Then it is a series of operations including foreground segmentation and a cascaded box regression process. For dynamic objects, the object track points are not aligned because we don't know the inherent motion between the frames of the object. So we take a sliding window approach to refine for each frame separately. For a given frame T, the input are the sequence object points from the nearby frames, as well as the sequence boxes. Because the boxes are smaller in terms of data footage, we can have a larger temporal context for the box sequence. Then we have two branches to encode the point features and box features before merging them to refine the box for the center frame. To notice that there are many other alternative designs, such as aligning the point clouds before refining it. Because we have a sequence, we may use the ICP-based method, trying to align the points to the center frame, so we'll get a denser point cloud, and then refine it. Or we can use a sync flow prediction model, trying to use a network to predict the sync flow, estimate the sync flow to align the points and then refine it. However, the alignment problem itself can be harder or as hard as the refinement process, especially for cases of occluded objects or when the viewpoint of the objects change aggressively. Another more advanced approach is to design a sequence-to-sequence model. Because we have a sequence of points, point clouds, or boxes as input, and the output is also a sequence of refined geometry as boxes. So we can potentially build a sequence-to-sequence model to process it. However, from our empirical experiments and trials, it is non-trivial to make them work as well as the current simpler formulation. We will leave more research to the future to develop more advanced this kind of 4D point cloud processing modules. So as the pipeline has many similarities to how humans label 3D objects in a sequence, meaning that they localize objects first, they track the objects across frames, and they try to go through the object tracks to give accurate and consistent boxes for each object. So for this pipeline, we call it 3D auto labeling in comparison to 3D human labeling. So our pipeline is trained on the Waymo Open Dataset and evaluated on the Waymo Open Dataset. So which is large-scale autonomous driving datasets, including more than 1,000 sequences of all sensor data. And we use the LiDAR point clouds for this experiment only. The model is trained on 798 sequences and evaluated on 202 validation sequences. So we show that our method largely outperforms existing detectors. The plot shows the 3D average precision at different IOU criteria. As the criteria gets more strict, meaning we use higher IOU threshold to determine a true positive, the harder the problem becomes and the lower the 3D average precision is. So we compare with two popular kind of onboard real-time detectors. One is the point pillar detector, which is widely used and very efficient. The other is a recent state-of-the-art detector called PBRCN. So here they are both single frame detectors in evaluation. We can see the gains are more significant at strict metrics, such as the average precision at IOU 80% threshold, where we see around 50% gains towards PBRCN single frame detector and more than 100% gains towards point pillars, validating the high quality of our auto labels. Here we also show some more complete evaluation results comparing with more methods, including some multi-frame detectors. Because the whole pipeline is based on the initial states of detection and tracking, so the base detector in the pipeline is also important. We're glad to show that our base single frame detector has already outperformed our prior published methods. By adding more frames, stacking more frames to the detector input, we can further improve the detector, as well as using the test time augmentation in this case called TTA, where we rotate the point clouds several times and ensemble their output results. So this further improves the detection. And lastly, more importantly, even on top of this very strong multi-frame detector, our whole pipeline, which included this object-centric refinements through object tracks, we can see further large improvements, where on the vehicles, we see a further around 5 points gain in the average precision. And even more on the average precision at a higher standard at 80% IOU, where the gains is more than 8 points. It also applies to pedestrians, although the improvement is not as large as that for vehicles. So remembering that at the beginning, we want to pursue a model that outputs near human quality perception. So with this high performance, we want to understand how far we are from human labels. So we did a human label study on 3D object detection. We selected a few run segments from or sequences from the Waymo Open Dataset, and we asked 3 different labelers to independently relabel each sequence from scratch. So here is a visualization of labeling results from 3 different annotators on a sequence, one of the frames of the sequence. So we see that although humans agree in most cases, as the 3 different colors indicate boxes from 3 annotators, there are still inconsistencies among them. For example, sometimes their box geometries are not as the same, or sometimes there are some record differences, as shown here. So we can also measure the average precision of human labels. So if we consider the original ground truth in the Waymo Open Dataset as the golden ground truth, and each human as a prediction, then we can measure the human average precision by ranking their annotations with the number of points in the box or distances of the boxes. Then we can directly compare human performance and our auto-label performance on the Waymo Open Dataset. So we found that auto-labels from our pipeline have achieved on-par results as humans, actually. So looking at 3D average precision of vehicles at IOU 70%, so our auto labels is just 1 point shy from the human labels. And if we look at the bird's eye view AP at 80%, auto labels actually even have slightly higher average precision than humans. So this is very encouraging. So with such high quality, a natural application is semi-supervised learning, meaning that we can use auto labels to train some student models, trying to improve their performance. These auto labels or pseudo labels can be mixed with some smaller set of human label data. So one application is in the low label regime. So considering this experiment, where we compare the student model performance when it is trained on 10% human label, meaning 79 sequences in the training set, and using 100% human label, meaning 792 sequences in the Waymo Open Dataset. 89 actually, 98 sequences. Notice that even with 10% data, there are a lot of frames because in each sequence we have 20 seconds and 10 hertz. But we still see a large gap between the 10% trained model and 100% trained model caused by the low label regime. But if we can train the offboard perception pipeline on the 10% data, And then we use this pipeline to auto-label the rest of 90% data to train the student model. We see the gap caused by reduced human labels is largely closed. In other words, using 3D auto-labels in this case can lead to roughly 10 times data efficiency boost in the low-label regime. Our pipeline can also be used to help the student to better generalize to a new domain in the case of unsupervised domain adaptation. So in this case, the old domain is the Waymo Open Dataset main data, which is mostly sunny weather in the Bay Area and in Phoenix. And the new domain is mostly rainy weather in Kirkland in Washington state. So we see that evaluated, so when the model is trained on the old domain and tested on the new domain, we see that the model performance drops when in the left bar, the student model trained on human label dropped from like 60-ish to below 60. But if we can use the offboard pipeline, which is also trained on the old domain, but used to auto-label a set of unlabeled sequences in the new domain, and train the student model with the mixture of old domain human labels and new domain auto-labels, we see a significant gains of the student model, increasing the average precision by 4.8 points. So we believe there are more applications to be discovered for the offboard 3D detection. And now let's take a look at some visualization results. Hopefully you can see the video. So we can see the boxes are really smooth across time, and the static vehicles have very stable bounding boxes. And this is a very busy intersection where we can see the headings are very accurate of the turning vehicles. Notice there are still some challenges for pedestrians when they are crowded or heavily occluded in terms of tracking them. And here's a parking lot with lots of static vehicles stably detected. Okay. So another application of offboard 3D detection is behavior prediction, actually. So we know that behavior prediction or motion forecasting is now a new frontier of autonomous driving research. And perception is used both in its training and evaluation. So to serve a focused study of the behavior prediction problem and trying to separate the perception noises from the problem itself, we leverage this offboard 3D object detection pipeline we introduced above to construct a Waymo Open Motion Dataset. More details is summarized in this paper called Large-Scale Interactive Motion Forecasting for Autonomous Driving, the Waymo Open Motion Dataset in this archive paper. Here I want to show some visualizations of typical kind of scenarios in this motion dataset, where this is a very busy intersection with lots of pedestrians and vehicles. And this is another case where we see some interaction of the car turning right and oncoming traffic. So Waymo also hosts a challenge and a leaderboard for those motion forecasting tasks. So we have concluded the challenge for this year in the CVPR, which happened quite recently. So you can check out more challenge results and winning methods in this talk. I put a YouTube link. You can also search it on Google and find a recorded video for this talk. And you're also encouraged to look at the data set and challenge. The leaderboard is still open for more submissions. To summarize, in this talk, we have introduced the offboard perception problem, and more specifically, introduced the first step towards offboard perception, where we build an offboard 3D object detection pipeline using point cloud sequences. And we noticed that the object-centric formulation is the key to the success, where we can leverage very long horizon temporal contexts to achieve close to human detection quality. There are a wide range of applications, as we demonstrated a few by using those offboard perception. For examples like assisting humans to accelerate their labeling process, using the offboard model outputs to train student models, and for unsupervised domain adaptation, or even creating other data sets, like for the case of motion forecasting. So it will be exciting and open for more research. So that's it for the talk. I welcome any questions you have or any comments or discussion. Thank you.
Thank you, Charles. We are open for any questions.
Thank you, Charles. My name is Dan from General Motors. And I was wondering, how do you see this task compared to online perception? Because you mentioned that there are modules you can share, but it seems here that it's two entirely different problems. Can you relate to that?
Yeah, sure. So remember that the pipeline is still built on top of the detection and tracking as the first steps, because we need detection and tracking to get object tracks, as shown in the top right figure. So those detectors and trackers can be easily shared with onboard ones. Although the detectors for the onboard ones may have more constraint, like in terms of latency and memory usage, but most of their kind of infrastructure and architecture can be shared. You can easily adapt the onboard ones to have just take more frames and have larger network and easily retrain it. And also the pipeline is modularly designed in the case it can hot swap its detectors. So whenever you have a better, stronger detectors in the future, you can swap that detector into the pipeline and you can kind of for free get better results. Yeah.
Thanks, great work.
Yeah, you're welcome.
I have one other question. How does your pipeline work for objects which are not very common in the street? So some lost cargo, for example, or other rare objects. Does your offline pipeline also help there?
Yeah, good question. Yeah, and also thanks for the comment in the chat room. I appreciate it. So long tail or rare cases we know that for people who work in the industry, we know that those are the really challenging and hard cases that we need to solve in order to achieve autonomy. So that's it for offboard perception or onboard perception. So that's where the modular design helps. So because we want to share, that's also a reason behind why we want to share some modules with onboard. Because for onboard, we need to solve those long tail rare cases. So the detectors trained on onboard, or the detector using the frame infrastructure or data used to train onboard, can be shared with the detector trained offboard. So that whenever you have detector that trying to kind of tackle those rare cases through data or model, you can also use this similar detector for the offboard cases. So in that way, if you can recognize and localize those rare objects, then the refinement module, which is more generic, can be still used to refine its geometry, especially for kind of leveraging the temporal context to select the best viewpoints and to leverage the dense points. So those are more generic. And the harder part is actually the localization step, which is the backbone detector. And again, it can be shared with onboard. Yeah.
All right, thanks.
Yeah, no problem.
Maybe just another small question.
Sure, yeah.
So theoretically, you could further improve the refined detector using semi-supervised learning on the offline detector you showed. Have you tried this? It can even bring results higher.
Yeah. That's a very good point. So you can actually do these iterations where you have a more powerful offboard pipeline. You're trying to use this pipeline to improve the itself, including detector and also the refinement step. So we don't report results in this paper, but we are doing such experiments, and we would like to share more results in the future.
Okay, thanks. Looking forward.
Hello, Charles. Thank you for your presentation. This is Walter from TU Munich. Did you try to use camera, for example, to further enhance the detections?
Hi, Walter. Yeah, that's also a great question. So although this work focused on LiDAR, so there's no constraint to use other sensor data. And of course, I think camera data will be very helpful to improve the detection quality. It will improve a lot. It could improve a lot for pedestrians, as other kind of leaderboard method has shown, especially when pedestrians are smaller and having less points. So it's harder to localize. I would argue that it also helps improve vehicles, especially for those ones with special color patterns or special kind of geometry. So the answer is definitely yes. A multi-model system, both in the detector stage, tracking stage, and the refinement stage can help the pipeline.
Okay, thanks.
So if there are no more questions, I suggest we move on to the next talk. So thank you again, Charles, for the presentation.
Yeah, thank you all.